Columbo and bodies in the pool.
My name is Lieutenant Columbo. Got two floaters in the pool, but this electrocution accident story is selling me. Smells fishy. I got a question for you brainy physics fellas. This picture was sent to a friend's phone that same day. I need to know what would be the worst effect on these folks in case that power strip takes a dive.
First, we need to collect some data. We found a list of effects for different current levels. To answer the questions, all we need to do is figure out what this effect would be in the worst case, right? A Google search for the average resistivity of the human body rendered 5 ohms per meter. And this other table may come in handy. It is not that water gets electrified and the victim fries Hollywood style amid sparks and explosions. To get an electric shock, there must be an electric current flowing into and out of the body. When the strip gets immersed, current will start flowing through the water from one contact to the other. Currents will be very intense near the power strip but will weaken with the distance. Current will not only flow through the water but will flow through the bodies of those folks as well. What we need to determine is how much. For that, let's focus on the origin of this current pattern. That is, focusing on the socket. Exactly on the conductors inside the socket and the electric field around those conductors. Once immersed in water, the current will follow the electric field pattern. The plastic cover of the power strip is an insulator that will help confine the currents to the space inside the strip and would only exchange charge through the holes. However, since it's a worst case scenario was being requested, we will assume that the set plastic is just up there. If there were only 2 contacts, all the current that flows out of one goes into the water of the pool and is then collected by the other. But there is a third contact in the socket, the ground. This may suck good part of the current, not allowing it to go out of the plastic cover. But again, being this a worst case scenario, we will assume it's not there or just not connected to ground. The power strip in the picture seems to have 5 sockets. But to make sure it's the worst case, we will assume it has 6, like this one. So whatever current we calculate for one socket must be multiplied by 6. Since no current can flow out of the water, one that flows out of a point near its surface takes a pattern like this. It will be the same pattern as if another identical current will be flowing out of a point equidistant to the surface. When the power strip goes under the water but stays near the surface, it will have the effect of 2. So multiplication will be by 12, not by 6. Here's the expression for the electric field of a dipole P when the radius vector indicates the position far from the charge distribution that generates it. At a distance d on the plane of symmetry, the dot product of P with the radius unit vector is 0. Then the expression for the electric field reduces to this one. On the other hand, at a distance d, this time along the axis, both P and the radius vector align, and so the expression reduces to this one. So we can conclude that at the same distance, the electric field on the axis is twice as strong as on the symmetry plane. Hence, for a worst case, we will assume the victim on the axis. Obviously, we need to figure that dipole moment P. And here's the definition. Well, the lowercase q is the charge density at point P. For the case of two parallel plates with charges of different signs, contributions of the components of R other than those along D cancel each other, and the integral reduces to a total charge Q that multiplies vector D. We may use the Gauss law for calculating Q. When the spacing D is much smaller than the plate dimensions, Q has this quite familiar expression. Because this is usually the first exercise of Gauss' theorem on every book. But that is hardly our case, since the plate dimensions are very much comparable with the spacing. The expression neglects the fringing effect of the electric field, so it underestimates the charge Q. However, we don't even need an estimate, but just an overestimate. At the center of the plates, the electric field must align with D, and so its intensity E must be the voltage over this distance D. It will then weaken to the borders and more so to the back. So if we integrate this maximum value of E over the entire area, including the back surface, we will certainly be overestimating Q, right? And finally, here's the expression that overestimates P. Now that we have an expression that we know P won't be greater than, we can replace it in the one for the electric field. Allow S to be the geometrical mean of the three dimensions of L, H, and D of the contacts. Replacing S in the expression for the electric field and dividing it by the resistivity, we get an upper limit to the contribution of the current density due to one socket. But there's 6 in the power strip and 6 more on the image. The total current density will not be greater than this. Time for some numbers. The line voltage in the United States averages 120 volts. The dimensions of the contacts on the socket are those there. That in the picture is a 15 feet plastic pool. Being the strip beyond the center of the pool, the distance to the victims should be greater than 7.5 feet. But say we got just 7 or 84 inches. Yet, to get anything out of this expression, we need the resistivity of the water. What would be the current density where these folks are? For that, we can use the expression we just derived. Now we can look up the resistivity in that table, the one that might come handy. Pools are filled with tap water, and then some extra chlorine is added. Resistivity must be then around its lower limit. But let's make it half that, which would make it equal to that of a human body of 5 ohms meter. Evaluating. Since the resistivity of water has been assumed equal to the human body, the current density through the body of those folks will be the same as in the water. The cross-sectional area of the human thorax is about 1/9 of a square meter. So the total current at 7 feet will be 0.15 milliamps. So it is way below the barely perceptible level.
How near the power strip this guy had to be for getting killed?
How near to be lethal? For that we need to go back to the current density inequality. We were using the resistivity of the water as 5 ohm meter. Now we isolate D and get this expression. The table refers to wire grabbing, or in other words, the effect of a current entering the thorax from a hand and exiting through any other limb. The cross-sectional area of the thorax is about 1/9 of a square meter, so the current density in those units will be 9 times the current I for each effect. Now we can create a new table more focused on the case at hand. Beyond 45 inches, they won't even notice that the power strip has emerged. Closer than 31 inches, they might start feeling something. This near, they may jump back and start yelling. Closer, some ridiculous dance moves may be expected as they hop away from the power strip. Respiratory paralysis, that may be lethal in the case of wire grabbing, when the victim can't let go and may asphyxiate. In the pool, there's nothing to grab. These two last effects would require swallowing the power strip. That leaves fibrillation at 1 foot as the only possible killing situation. To be nearly fatal, the victims had to be much closer than this, with their thoraxes immersed in 4 feet of water at the time the power strip submerged.
The accident story's getting tough to swallow, right? Just one more thing. Is this really worst case? What if the pool had too little or too much chlorine?
Too little chlorine would have increased resistivity of the water, making all currents smaller, both in the water and the bodies as well. On the other hand, if the resistivity of the water decreases below that of the body, the currents will be stronger, but it will be shunting around some of it. Too much chlorine will certainly make the current stronger, but it is doubtful that it gets as bad as seawater, which is 50 times more conductive. This doesn't mean that the body takes a hit that much stronger. It can be proved that it only increases 1.5, making the lethal distance grow a couple of inches. You got yourself a crime scene.
Yeah, there's been foul play here. The scene is being taped as we speak. Great help, you guys. I'm out of your hair.
This is Armando Rodriguez, and I'm afraid this has been already too much physics. If so, it's time to say goodbye. Otherwise, stay for Lieutenant Columbo has one more thing.
Not so fast. If it can be proved, then prove it.
Well, you're asking for it. Tighten your seatbelt. Then we'll have to study the human body when immersed in a uniform current flow. It would be very similar to that of studying a sphere within a uniform current flow. Two charges of opposite signs can generate a uniform electric field, and here's how. Consider the electric field of those charges at a point on the z-axis. The resulting field can be expressed as shown. Now allow the charges to fly apart. At a far enough distance, z becomes irrelevant. As the q's fly apart, if they grow with the square of d, the electric field E will stay constant and uniform in an ever-growing space around the origin. Now's a good time to recall the well-known problem of the point charge and the grounded sphere. The ratio of the negative image over the original charge equals the ratio of the sphere radius over the distance. And the distance of the image to the center over the radius equals the same ratio. Now we insert a conducting sphere between the cubes. As the cubes fly apart, their images in the sphere fuse into a dipole, the moment P of which can be expressed in terms of the electric field E. Let's see how. From the charge on the grounded sphere, we have these two equations. This allows replacing the d prime and the lowercase q with the external charge q and their distances. But q also relates to the applied electric field, so finally, Here's the dipole moment in terms of the electric field applied. By the way, this sphere need not be grounded, for it always stays neutral and no charge needs to be exchanged.
Will you please remind me what was it that we were proving here?
We're proving that no matter how conductive the water, the current through the body would not go beyond 1.5 of the case of equal resistivity that we had considered.
Right.
The surface charge of the sphere generates the following: a dipole field outside the sphere, and a uniform field inside that is equal and opposing to the applied. When we superimpose this to the applied electric field, we get this field pattern. But what if this happened underwater? Outside the sphere, there will be a pattern of currents in proportion to the resulting field vector E. But what about inside, where the intensity of the field is zero? Currents cannot just vanish at the surface of the sphere. True that the electric field E is equal to zero there, but also the resistivity rho. This is a limit situation. If we step back and said that rho is a very small r sub b, but not zero, the surface charge near cancels the electric field, but not quite. Whatever is left will then allow an expression for the current density. Now, instead of the surface charge dipole moment being proportional to the applied field, the surface charge dipole will be proportional to the field inside the sphere, E sub b. The current density inside the sphere will be uniform and equal to the superposition of the external field and that of the surface charge. The current density outside the sphere, JW, W for water, will be the superposition of the external field and that of the dipole created by that surface charge. We are using the sphere as a simplification of the human thorax. Those B's in the subscripts stand for body, the human body. The current coming through the sphere must be equal to that coming out of it. Being the current through the sphere a uniform flow, it integrates just as the current density by its area. The current out of the right half of the sphere involves real integration over its surface. The expression for the current density in water? There it is. We replace it as the integrand. Let's separate the two integrals. The first term is straightforward, for E is uniform. The current density multiplied by the area of the sphere. The second, that may take some work. Okay, we were here. This is the expression for the electric field of a dipole. And this is the one for the dipole moment in terms of E sub b. Replacing the dipole moment with its expression, we get to the integrand. Let's separate the integral in two. Hello, here's another easy one. Rearranging. Are you still with me here?
Yeah.
Okay, now's the time for doing the surface integral over the right half of this sphere. We can use the surface differential as a ring around the system's symmetry axis. We can now replace the dot product of the two unit vectors by the cosine of the angle between them, and the surface differential with the expression in the drawing. We rearrange, and noticing that the cosine of zeta d zeta is the differential of the sine, we can change the variable. That is, sine of theta by x, and the integral limits to 1 and 0. This is just the area on the straight line between 0 and 1, which is just 1/2. Which ends up with this expression for the current going out of the sphere. And this must equal the current coming through the sphere, which we already had. We equate both expressions and making a little magic with algebra. And we get to the equation that can explain everything about electric shocks and water. Let's consider a first case in which the resistivity of water is much greater than that of the body. The expression reduces to this one on the right. This is the case of a pool with very clean tap water. The total current through the body can be up to 3 times greater than through the same area of water. Though the body gets a greater share, the current densities due to the line voltage in a power strip would be very small. However, if lightning hits the pool, this would be the very worst case, since the vault has no shortage of volts. The second case would be the one in which the water in the pool has nearly the same resistivity as the human body. Here, the presence of a body in the water has little effect on the flow pattern. This is what we originally considered was the case of the pool with the dead bodies. And there's a third case, the pool with seawater, which can be up to 50 times more conductive than the human body. Surprisingly, lightning is more forgiving in seawater, for its killing radius is 10 times smaller than it would be on a lake or a pool. Still, it's 20 to 40 feet, so you better get out of the water. Finally, this expression proves the point. A shock from a power strip will not be 50 times stronger, but only 1.5, and may add a couple of inches to the killing distance. That's it.
That's the kind of answer I was waiting for. My gut was telling me this was no accident. The guys were murdered somehow and dumped in that pool. I had to make sure though, because in the movies, killer had done people this way. You better not go with what you see in the movies. Okay, thank you guys. I'm out of here. Can some guy give me a jump start?
This is Armando Rodriguez again. I hope that following this case, you've learned a thing or two about electricity and water. If so, subscribe to the channel